So previously we got familiar with spherical coordinates, how we can use them to describe space, um, and how we can convert between rectangular and spherical coordinates. So now we're going to take a look at integrating with spherical coordinates. Um, so the main trick that we need to uncover, as we've seen previously, is how to convert the differential part of the integral. So previously, we saw how we can convert dx dy to r dr d theta, and that allows us to calculate integrals in polar coordinates and also in cylindrical coordinates. So now we're going to figure out the same conversion for spherical coordinates. So there's a couple different ways that we can do the conversion. So one way is to do it geometrically. So in the picture, we can see that there is an R1 and an R2, and then we sort of take the space between those. Then we've got, there we go. Then we've got a theta1 and a theta2, and then the little space between those is a delta theta. And then measuring phi off the z-axis, you've got a phi1 and a phi2, and then the space between that will be a delta phi. Okay. So that making all with all those three deltas, that gives us this solid object, and that's called a spherical box. And we could think of it as a little bit of volume, and so we call that delta V. So what is delta V? So doing some calculations, and from basically the formulas for the volume of a sphere, we can reduce this down to delta V equals 1/3 minus R2 times R2 cubed minus R1 cubed times cos phi1 minus cos phi2 times theta2 minus theta1. And by doing some factoring and rearranging, we get that delta V is approximately R squared sine phi times delta R times delta theta times delta phi. Now, you look at that equation and you may say, where did that come from? It looks like some steps were skipped. That's true. In fact, a lot of steps were skipped. This calculation turns out to be fairly lengthy and involves quite a bit of tricky algebra. So the calculation I'll just leave for elsewhere rather than going through every step. Okay. So, but instead, what I'd like to focus on is just where this formula comes from using differentials. So we have our, so recall that we've got a solid rectangular box, delta V equals delta X times delta Y times delta Z, your basic bit of volume, delta V. Okay. Now, a spherical box, as in the picture, comes from the changes in R, theta, and phi. So let's look at the dimensions of the spherical box. So the spherical box, the height of it here's a spot for R1, here's a spot for R2. The height actually is delta R. So that part's good and straightforward. However, the other sides are not measured by just delta theta and delta phi. We've encountered this before with polar coordinates. So let's take a look. So as we discussed previously, let's look at the arc with R and theta fixed. So R and theta fixed means we've got a delta phi. So that arc comes from going from here to here. So that arc is part of a circle of radius r, technically r1. So therefore, and the angle is delta phi, therefore the length of that arc is r times delta phi. Next, we've got the other arc that's got r and phi fixed. So r and phi fixed means that the side means that it's determined by delta theta. So that is starting here, going here, that side right there. That's determined by the delta theta. So remember that with phi fixed and theta varying, that's going to make a circle with radius r sine phi. So since that's the radius and the angle is delta theta, the length of that arc piece is r sine phi times delta theta. So now that we've got those three dimensions, we can put them all together in order to make the volume. So the volume of the spherical box is approximately the volume of a rectangular box. Multiply those three things together. So therefore you get delta V is approximately r squared sine phi, delta r, delta theta, delta phi. So just like with polar coordinates, the fact that we can take these rounded things and approximate them as straight is true, but proof of that is beyond the scope of our discussion. So we can now turn this approximate statement into an exact statement using infinitesimals, and we get dv equals r squared sine phi, dr d theta d phi. So that is the conversion formula for differentials. So one comment about that, notice that this is starting to get a little bit tricky to convert between with a change of coordinates to convert the integrals. So it turns out that there is a method of calculation to transform the integral for coordinate transformations as a general formula. So development of that requires a bit more math than is covered in this course, but it is discussed elsewhere. So now that we've got this, let's get into seeing how it can help us in a problem. So, example, let's calculate the triple integral over some solid b dv, where b is the upper half of a ball radius 1, centered at the origin. First, we're going to do this in rectangular coordinates. So two things. First of all, notice that the triple integral of dv is just going to give us the volume. And secondly, what is the thing that we're actually integrating over? So on the right side here, there's a little sketch. So it's basically a solid sphere, but just the top half. Okay, so in rectangular coordinates, the hard thing is we've got to set up the boundaries. So what are the boundaries? So the first thing to note is that the relatively straightforward boundaries are for z. The smallest value for z is 0, and the biggest value for z is 1, since the radius is 1. Now, at a given z value, I've got that little dotted line in here. Notice that it makes a circle, or a disk, I should say. And if this is the disk, notice that the height is z, the radius of the sphere is 1. So this side is the square root of 1 minus z squared, and that is the radius of that disk. So because that's the radius of that disk, then we can look at y. And we know that y is, on any given slice, y is at most square root of 1 minus z squared, and then at a minimum negative the square root of 1 minus z squared. So once we have that by a similar slicing procedure, we can get at a given z value and given y value, x, the boundaries for x are going to be the square root of 1 minus y squared minus z squared on top, and then the negative of that on the bottom. So that tells us how to set up the integral. We put in all our boundaries for x, for y, for z, and then we just integrate. There's no function. Integrate dx, dy, dz. So first, integrate dx. Integrating dx just gives us x, and then we have to evaluate on the boundaries. So we're going to have the radical minus negative of the radical, so that just gives us 2 times square root of 1 minus y squared minus z squared. Putting the coefficient 2 in front. Now we have to integrate this dy. It turns out that this is actually quite a difficult and complicated integral to do. So either using software or a table of integrals, skipping the details, we get the result of the integral is this. 1/2 y times radical 1 minus y squared minus z squared plus 1 minus z squared times arctan of y over rad 1 minus y squared minus z squared. And now we've got to evaluate that on the boundaries. Again, that's a pretty hard integral. You can do it by hand, but it's actually quite hard. Plugging in, things cancel, and you actually wind up with pi times 1 minus z squared. So finally, we have to do this integral. And that's pi times z minus z cubed over 3. And now we need to evaluate it as z goes from 0 to 1. So plugging in, we get 2 pi over 3. Now, doing it that way, that is if we do the integral staying in using rectangular coordinates. Clearly, this is a challenge. First of all, it's a challenge to find the boundaries. Second of all, it's a challenge to do the dy integral. Now, let us apply what we just learned, and let's try to do this in spherical coordinates. So, what are the boundaries? So, I should say we have to look at two things. First of all, we need to know what dv is, and second of all, we need to set up the boundaries. So we know what dv is because we just came up with the formula for dv in spherical coordinates, first of all. Second of all, what are the boundaries? Well, we've got a sphere, but just the top half of a sphere. So it's a solid sphere. So the radius, the smallest radius is just at the origin at 0, and it goes all the way out to 1. So the boundaries for r are 0 to 1. Next, this thing sweeps relative to the xy plane, it sweeps all the way around. So we know that theta is going from 0 to 2 pi. What about phi? Remember, phi is measured off the z-axis. So, the positive z-axis. So positive z-axis definitely included, all the way down to the xy plane, which gives an angle of phi equals pi over 2. But notice that we don't want the bottom half. So we don't want phi to go past pi over 2, and those are the boundaries. So put it all together, and that gives us this integral. And note that because the boundaries have constant values, we could, and the function is fairly straightforward, we could do the integral in any order. But I'll just leave it like this. So first we integrate dr, and that gives us 1/3 r cubed, r going from 0 to 1, and the sine phi hangs out. Plugging in, we get 1/3. So just got 1/3 sine phi, and now I've got to integrate d phi, and that gives us, keeping the 1/3, and then we get negative cos phi. And then we've got to plug in, evaluate as phi goes from 0 to pi over 2. And that gives 0 minus negative 1. So that just gives 1/3. And now we've got to integrate d theta. And that just gives theta over 3. Evaluating from 0 to 2 pi, you get 2 pi over 3. So the main thing I want to point out here is this is our first integral using spherical coordinates. And in particular, notice how straightforward it was to do this integral in spherical coordinates. The main lesson is that because the object we're integrating over is a sphere or sphere-like, spherical in nature, we can set up the boundaries very easily, and in fact, they wind up being constant boundaries. Okay. And as a footnote, finally, because of the nature of this problem, since the triple integral over b dv is just asking for the volume, we can use our known formulas. It's just the volume of a sphere, but then just half of that because it's the top half of the sphere. So we know that this integral just equals 1/2 times 4/3 pi 1 cubed, and that's just 2 pi over 3. So we did our first spherical integral. Now let's kick it up a notch and do another integral, and we're going to use spherical coordinates. So find the total charge of a solid sphere radius 3 with charge density P equals 2xyz, and that's coulombs per meter cubed. So a couple things. First of all, this is an application, so we have to understand what it's asking and how to set that up. So let's get into it. So notice that we're being asked to find a total charge. So we're being asked to find charge Q. Now, how do we find the charge Q? Well, we're given the density function. How do we find total charge given the charge density? You integrate your density over your space. So this is just going to be the triple integral over my space B of density P dV. And let's just double check the units on this. The density P has units coulombs per meter cubed. And then dV is a small bit of volume, so its units are meters cubed. Multiply those together, and you'll just get coulombs, which is your charge. So we know the basic idea for the integral. Now we've got to sort out exactly how to set it up. So what is this? There's going to be a triple integral. So the first thing I want to do is I'm going to set up the function first. So what is the function? The function is going to be 2 times x. Well, we know how to convert from rectangular to polar coordinates. We know that x equals r sine phi cos theta, and y is r sine phi sine theta, and we know that z is r cos phi. So we've converted the function. Next, we need to convert dv. We have the formula for that. We know that dv just equals r squared sine phi dr d phi d theta. Okay. And next, we just set up the boundaries. So this is a solid sphere. So to get around a solid sphere with radius 3, we know that the boundaries for r, smallest one is going to be 0, and the biggest one is going to be 3. And phi, well, let's say theta, we know it's a whole sphere, so we want to wrap all the way around. Theta is going to go from 0 to 2 pi. And for phi, it's a solid sphere, so we want to go from all the way to the top to all the way to the bottom. So the boundaries for phi are 0 to pi. So one of the hard things in adjusting to spherical coordinates is we're going to have to get used to thinking in terms of r theta and phi, especially for setting up the integral. Okay, but now we have written down the integral as we're going to do it in spherical coordinates. So now we just need to calculate it. So our first step is going to be, let's simplify and rewrite this. So we've got our boundaries, and combining everything, we get there's that coefficient of 2. So I'm just going to put that coefficient in front. And then collecting all the r's, I've got r to the 5th. And then there is sine phi, sine phi, sine phi. So I've got a sine cubed phi. And then I've got a cos phi. And got a sine theta, cos theta. dr, d phi, d theta. Okay. So there's the integral simplified. Now again, we could integrate this in any order, and it turns out this is not the optimal order, but that's not obvious. So I'm just going to go ahead and integrate it in this order as if I didn't know any better. Let's just go ahead and do it. So keeping the 2 on the outside, 0 to 2 pi, integral from 0 to pi. Let's do the integral dr. So this gives, I'm just going to put the trig functions. I'm going to keep the phis and the thetas. So integrating the r bit, so that's all a constant relative to r. You just get r to the 6th over 6. And plugging in as r goes from 1 to 3. Okay. So plugging in, we're going to get so plugging in, we'll wind up with 243 over 2, but times 2. So you'll wind up with 243 as a constant. And then with all the trig functions intact. So now we integrate d phi. So to do that, we can just do a simple substitution. U equals sine phi. So du is just going to be cos phi d phi. So doing that integral will give us see, so the thetas will just sit there. So sine theta, cos theta, and that's just going to be, so this is integrating u cubed. So integrating that is just going to be u to the 4th over 4. So that's just going to be sine to the 4th phi over 4 as phi goes from 0 to pi. So plugging in phi equals 0, sorry, plugging in phi equals pi, sine of pi is 0, so that's just 0. Plugging in phi equals 0, sine of 0 is just 0. So put that all together and you just get 0. Well, if I'm integrating 0, that just gives me 0. So it's 0 coulombs. Okay. Now, first of all, so as a note, why is it possible to get 0 coulombs? Well, we're measuring charge. Charge can be both positive and negative. So what all this tells us is that the positive charge and the negative charge, all in all, cancel each other out. But then also, finally, this is how we do a sort of more complicated integral in spherical coordinates, paying attention to 3 things. First of all, we have to set up the boundaries properly. Second of all, we have to, since the function was given in rectangular coordinates, we have to convert that to spherical coordinates. And thirdly, properly setting up dv, or recognizing we need dv and converting dv into the spherical coordinate expression.